The result of a scalar projection is a scalar and does not contain direction, as the name suggests. The previous video mentioned that scalar projection is essentially a coordinate. For example, the scalar projection of vector A onto a non-zero vector B is the coordinates of A's orthogonal projection onto B. Conversely, the scalar projection of vector B onto a non-zero vector A is the coordinates of B's orthogonal projection onto A. Imagine a beam of yellow light passing through a red filter. Only the intensity of red component is preserved. This intensity value can be compared to the scalar projection of the vector yellow onto the vector of red. The yellow light vector is 1, 1, 0, and the red light vector is 1, 0, 0. The scalar projection of yellow light onto the red light vector is 1. Conversely, the scalar projection of red light onto the yellow light is square root of 2 over 2. We know that the length of yellow vector is square root of 2, and the red light accounts for half of it. Now let's look at vector projection. Vector projection is the product of coordinate times direction vector. This direction vector is the unit vector in the projection direction. For example, the vector projection of A onto B is the scalar projection of A onto B multiplied by B's direction vector. On the other hand, the vector projection of B onto A is the scalar projection of B onto A multiplied by A's direction vector. The vector projection of yellow light onto the red light vector is simply the red light vector 1, 0, 0. Now, think about this. What is the vector projection of red light onto the direction of the yellow light? When the yellow vector is orthogonally projected onto the red vector, there is still some left over. This remaining part is the green vector. The remaining green vector is perpendicular to the red vector. Simply put, green vector is the part of the yellow vector that the red vector just can't account for. In vector projection, this green vector also has a name. It is called orthogonal complement, also known as orthogonal remainder. In the diagram, the pink vector is the orthogonal complement of A in the direction of B. Clearly, this orthogonal complement is perpendicular to vector B. This diagram also shows that vector A can be decomposed into two components. One component parallel to B, the other perpendicular to B. We call this the orthogonal decomposition of a vector. The white light vector can be orthogonally decomposed into yellow light, blue light. Clearly, blue light is perpendicular to yellow light. Similarly, a white light vector can also be orthogonally decomposed into magenta light and green light. In RGB space, we can find nearly infinite decompositions of white light. Vector decomposition can be understood as the inverse operation of vector addition. It splits the vector into two or more components such that their sum equals the original vector.